In today's lecture, we will see what are the problems a priori algorithm can face and how we can improve this efficiency of a priori algorithm using some of the techniques. Now let us see. Uh, these are the problems and these are the major computational challenges that a priori method needs improvement, okay, for this kind of challenges. Say multiple scans of transaction database, so we will see that how we can reduce this whenever the number of scanning in the database, transaction database is higher, or the data volume of data in the transaction database is higher, how we can improve it. If the number of candidates is huge, how we can improve the a priori algorithm by implementing few of the modifications, right? Or say TDS workload of support counting for candidates. So these are the major computational challenges area, and some of the ideas of this improving a priori algorithm are these 5 techniques we are going to learn. First comes hash based technique, then transaction reduction, partitioning, sampling, and dynamic item set counting. Okay, so we will just see one by one how this improvement works. Now you can understand easily what this hashing technique is doing. You can see here, if we follow the table that we have seen in our previous class, let us revisit that one. This one, okay, just remember the table here. Now you can see from this table we can count the occurrence of I1, we can count the occurrences of I2, I3, I4 and I5. Fine. So after counting all this, you can see here this whatever the bucket address is, we have marked the bucket address starting from 0 and ending at 6, and these are the bucket counts. Means why we have done it from 0 to 6. You can see here the hash function that we are using is following the modulo 7 pattern. So modulo 7 pattern can result either 0, 1, 2, 3 or 6. You can use this hash function as well, or you may modify the hash function as per your need. Okay, that's why 7 buckets are there, ranging from 0 to 6. Now these are the bucket counts. Okay, first is 2, then 2, 4, 2, 2, 4, 4. Okay, so here the hash table H2 for candidate 2 item sets. Okay, this has been done for 2 item sets. You can see here the total number of item sets in any of the whatever the bucket content is, it is having two items in each of the set. So it has been done by scanning the transactions, and if the minimum count is 3, okay, then if we set this minimum count as 3, and this has been done by the process of counting, that whenever the bucket count is 2, and you can put it here that the order of x multiplied by 10 plus order of y mod 7. If you perform this hash function on all of the items, right, so then we can decide in which bucket it is going to be placed. Okay, so based on this hash function we can place my item set in that bucket only. And now you can see here that after placing this, say for I1 and I4, we will put x equals to say 1, we will multiply it by 10, then y equals to 4, and then again means after that the total value will be modulus 7. So in this fashion we have put it this item set in their buckets as per the bucket address, it is 0 to 6. Now we will mark the count. Okay, see, you can see that bucket 0 is containing 2 item sets, so the count is 2. Similarly, bucket 1 is containing 2 item sets, again the count is 2. For the bucket address having 2 value, it is having 4 items, so the count is 4. So in this fashion we have we can perform the count. Now if we just set the minimum support count to be 3, you can see here in one iteration or in one time we can discard bucket 0, we can discard bucket 1, we can discard bucket 3, we can discard bucket 4 as well, right? So now we are having only bucket 2, we are having only bucket 5 and 6, right? So you can see that this hash based technique, this is a very simple hash function. It's a linear hash function only. So in linear amount of time we are going to place all the 2 item set. You can perform it for 3 item set, 4 item set, whatever the requirement is, and you have to change the hash function accordingly. So based on this hash function we can perform the count of the items at very very efficient manner, and obviously it's a great improvement technique, and it reduces the number of candidates as well if we compare this to the traditional a priori algorithm. Okay, next one, this transaction reduction method says a transaction that does not contain any frequent k item sets cannot contain any frequent k plus 1 item set. So you can easily understand that, say we are having some of the items marked as A, B, C, D, E, right? And now if we are in search of a pattern A, B, C, and we failed to find that pattern ABC. Now if we add one more item ABCD, definitely we are not going to find that item because ABC is not existing. So whatever the item, whatever more items we add to it, to that frequent pattern, definitely we are not going to find it off, right? So therefore such a transaction can be marked or removed from the further consideration, because subsequent database scans for J item sets where J is greater than K will not need to consider such a transaction. So whenever a pattern, say whenever we are finding out 2 item set pattern, and if one particular pattern is it is not frequent, right? So say AB is not frequent, so we will discard that only at that time, so that we do not have to generate any other patterns which follows AB, because if AB is cannot satisfy this minimum frequent count limit, then whatever the item we keep on adding with my AB, it is never going to pass that minimum frequent count. Okay, so we can discard that at that level only, so that no more counting or no more headache of that particular pattern remains with us. Now say what we were talking of a large database, we were talking of large number of candidates. Now see, this is a very beautiful technique. What we are doing, we are partitioning the database into n partitions. You can set n as per your requirement. You can see the flow chart there. In the transaction D, we are feeding it to different n partitions, and we are dividing the total D set into n partitions. And what we are doing here, you can see, say we are having 5 different partitions, right? And we can perform this scanning operation parallelly in 5 different partitions, and we have set my minimum frequency count, and we can come up with those item sets which are qualifying my minimum limit, and I am combining this all local frequent item sets to form a candidate item set, right? So you can see here, instead of scanning the whole database, if we can partition it and can perform the scanning operation parallelly and can come up with those item sets which are satisfying the criteria in its local area, and then can come up with this total item set. And now we can in this phase, this is a phase 1, and if we can find out all the qualifying item sets from its local area, then we can find the global frequent item sets among the candidates, among this qualified candidates from the local candidate set, right? So this will enhance my or it in smaller amount of time, or in more efficient way we can perform this scanning part, and so that we can come up with the frequent item sets in smaller amount of time. Okay, one more method says this sampling for frequent patterns. It is doing what? Say we are having a huge number of candidates and we have to perform this a priori algorithm. Okay, it will behave similarly like a priori algorithm, but instead of performing or instead of applying this a priori algorithm on the original database, we are going to take off a smaller sample. Okay, means we are going to select a sample amount of items from the whole database, and then we are going to perform my a priori. Okay, now again, I after this after mining this sample database, or from which we have designed from the original database, and we are going to scan database once to find to verify frequent item sets found in the sample. So what we are doing, you can see that from the sample database we have find out, so we have collected some frequently occurring item sets, right? Now using those item sets we are going to find the frequent item sets in the total database. Now what is the meaning of doing like this? You can see in this case we can check the borders and we can come up with the original values. What it would be like, say if we performed a priorly, means from the beginning, if we have performed a priori, we have to scan two item set, two sized or two length item set first, then three length, then four length, in this fashion. But if we perform the total a priori, which I was talking of, that firstly finding out that frequent pattern using two length item set, then three length, then four length, and we have, if we can restrict that to that sample size of the database instead of the original one, so that database size is much smaller, right? So it will not consume much amount of time. That after applying that a priori to that sample database, we can come off with the frequent item set. Now whenever with the help of those frequent items that we are going to scan the whole database, we are going to scan only the borders. Like, see, if we can check for ABCD pattern, it is going to cover all the subsequences. As for example, it will already cover AB, it will already cover AC, it will already cover AD, it will already cover BC, it will already cover BD and CD, right? So instead of checking all these patterns AB, BC, CD, AC, AD, whatever are, if we can check it for ABCD totally, then all this will get checked automatically, right? But it is not possible without applying a priori to the sample database, because if we cannot come up with the frequent pattern from that sample database, how we are going to check it off? Okay, so this is again going to reduce my this mining time, right? So in smaller amount of time we can perform this, finding out this pattern matching. Okay, next this is a last technique which helps in modifying the a priori algorithm. It is called dynamic item set counting, and it reduces the number of scans. You can see here what it is doing. Here we are going to partition the database into different blocks. Okay, now you have seen that while we are partitioning the database into different blocks, we performed the scan in each database. We come up with some frequent patterns, and then we merged all the frequent patterns that the local databases or the partition databases generated. Then we performed again the frequent pattern in the total merged database, right, of smaller size. But here what we are going to do, after partitioning the database into different blocks, we are going to mark the database by its start points. Fine. Now what this method is doing, the new candidate item sets we can add at any start point, right? So here whenever a new candidate set generate, instead of putting it in the means after the total in a priori, what happens that, say, new candidate is generating, okay, but we are keeping those new candidate at one place. After the total scan occurs, then we can come up with the new candidate set. If you remember the a priori example, say whenever we were scanning for one item set, we were maintaining the count there. After one item set scanning is complete, then we moved to two item set, we kept the count there. Then after two item set gets completed, we move to 3 or 4 in this manner. But here what we are doing, since we are partitioning the database and we are marking each database using a start point, for the new candidate, whatever we are generating, we can put it in the database and before the total scan finishes. So what this is going to do, this technique uses the count so far as a lower bound of the actual count. So whatever count means right, so whatever counting means how much scan has happened, that is the actual count, but we are again maintaining a variable called count so far. Okay, so far I have counted this. Say there are items like I1, I2, I3, I4, I5. Okay, now the minimum criteria of eligibility is 2. Now we have counted that I3 has occurred, means we have found I3, 3 I3s there. Now we can see that I3 is already I3 is already satisfying its minimum criteria. So we are not going to count I3 anymore, because we have generated the new candidate, we have put it into the database, and since my count so far variable is already satisfying my lower bound criteria, so whatever the actual count of I3 is, we can keep on counting it. But for now we can put, or we can make I3 eligible. Right, so other I3 for now, for this iteration, whatever the occurrences of I3 are, we need not count those. Right, so you can see here that the number of scanning will reduce by a large number. Right, so if we can keep one more variable called count so far, and if it reaches the minimum criteria of to be eligible to a frequent pattern, before counting, before all the values or all the occurrences has been counted so far, and if we can if we can stop the counting there, if we can stop the scanning there, so my number of scans is going to get reduced by a large number. So this is one more technique of improving my a priori algorithm. Fine. So next we are going to see one more technique which is a much better choice than a priori, called FP growth, or frequent pattern growth approach. So in many cases, a priori candidate generate and test method significantly reduces the size of candidate sets, leading to good performance again. So this we have covered that, we have seen that how a priori algorithm can be improved and all, but still this a priori algorithm suffers from this to non-trivial cost, right? So you can see it still, after all these approaches what we have seen, it still may generate huge number of candidates set. You can see an example has been given here. Now it may repeatedly scan the whole database and check a large set of candidates by pattern matching. So whatever we are doing it, either we are doing it parallelly, or we are doing it dynamically, or we are maintaining hash table, or whatever it is, ultimately it needs to scan the database repeatedly. Because see, whenever it is scanning the database for one item set, it has scanned the whole. Again, whenever it is trying to find out the matching for two item set, again it is scanning the database, whole database, in whatever technique it is following. Ultimately it is scanning the whole database, right? So repeated scanning is there. So if we can come up with an approach that that it can do, means all the scanning can be done, or rather all the frequent item sets can be, we can come up with all the frequent item sets without such number of scans, or without scanning the database repeatedly. Can it be done? So we are going to see this one. This is called FP growth. Okay, so I'm just reading out the total steps, or whatever the steps my FP growth is going to follow, but I think it will be clearer more whenever we are going to see the example. Okay, so what it is doing, it is following a divide and conquer strategy. First, it is going to compress the database representing frequent items into the frequent pattern tree or FP tree. We will see a tree like structure there. Frequent item sets will be marked up there, that it will be represented there. Then it will divide the compressed database into a set of conditional databases, and this will you can see whenever we will perform the mining of the tree, we will see that how it is going to compress a database into set of conditional databases. Okay, and each will associated with one frequent item or pattern fragment and mines each database separately. Fine. So these are the techniques which we are going to encounter just now. So let us visit the example without further describing this process. You can see here this example we have already used for a priori, and we are going to solve this means the frequent, we are going to find out the frequent pattern using FP growth in this database only. Okay, you can see here here it needs the scanning. Definitely for the first time we are going to scan the whole database, and we are setting the minimum support count to be 2 in this case. Now see what it is going to do. You can see here there are total 5 items. One is I2, I3, I4, I5 and I6. Sorry, I1, I2, I3, I4 and I5. Total 5 item sets are there. And if we just count it off, I1 occurs 6 number of times, I2 7 number of times, and for 3, 4 and 5 you can see it. And we have arranged this total total set in descending order of their count. Okay, so you can see here from the beginning it is just keeping that item set which is occurring most frequently as a top priority. Fine, so it has been arranged in the descending order. Okay, now see the tree, so how it is acting. You can see here that we have counted the, we have scanned the database 1 and have come up with this value. Whenever the item ID is I2, its support count is 7. If it is I1, it is 6, and we have come out with this support count value, and we have ordered this list in descending order. Okay, so now you can see this total block or this total index is associated with one node link. So what it is doing, just now focus on the tree. We will mark the root node as a null. Then you can see here for the first one, that is that is our I2. Okay, now you can see here one I2 is having count 7, another I2 is having count 2, means the left child is having count 7 and the right child is having count 2. Do not get confused for now. Just discard this count and focus on the items only. So firstly we are marking this I2 as one of the child node of the root node, because I2 is having the highest count here. Okay, now let us go back to the this chart. You can see here for this first transaction ID, that is T100, what are the two more items associated with I2? One is I1, another is I5. Okay, let us go back to the tree again. Now just see the leftmost path, do not focus anywhere else. Okay, so I2 will have two more items, one is I1, another is I5. Do not focus on the count, just keep focus on the item only. We will see how the count is being generated. Okay, so I2 is having one child, that is I1, and I1 will have another child called I5. Okay, do not focus on the dotted line now, just see the leftmost path. Okay, so this branch has been created. Now see how we are finding out the count. Here if we consider the first transaction, that is T100, that's I1, I2 and I5, which contains these three items I2, I1 and I5 in L order, because why I2 is been followed by I1 and then I5, because I1's count is more. You see the original table, I1 is having 6 and I5 is having 2. So it is following this pattern: I2, then I1, then I5. Okay, just I'm talking of the leftmost path. Okay, so this is one of the path we have generated, and this is the first branch of the tree. Now since we have, you can see here, if rest of the tree, if you just discard the rest of the tree and this branch exists only once, so here we have included the node I2 once, we have included the node I1 once, and we have included the node I5 once. That's why you can see here the count is 1 for I2, 1 for I1, and 1 for I5. Okay, just remember this one. So since we have included this nodes once, that's why the count is 1. Now I2 is linked as a child to the root. Now I1 is linked to I2 and I5 is linked to I1. Done. In the second transaction, you can see in T200 it contains the items I2 and I4 in this order. So I2 is having a count higher than I4, so it will follow the order I2 followed by I4. Okay, and for this you can see again we are putting one more branch. You can see there in the diagram, we had I2 already with us, and we are putting one more, that is I4. Okay, you can see I4 as the as one more branch. You can see from I2 leftmost branch is I1 and rightmost branch is I4. So this has been linked to I2 as well, and it is having a common prefix I2. So now what will happen? The count of I2 will be incremented by one more unit. You can see here we have created the new node called I4 1, and it has been linked to already it is linked to I2. So we will increment the node I2 by one more unit. So it was I2 count was 1 and we have incremented it by one more. It will become 2 now. Okay, fine. Now as you proceed like this, say we have considered transaction with T100 TID and T200, right? And this 2, after including these 2, we have seen that the total count value is getting incremented by 1. So if you proceed like this, then you will have to consider T300, then you have to consider T400. So if you proceed like this, the time will come whenever you will see that all the values or all the counts has been changed. Okay, so here you can see that ultimately the count of I2 will become 7, the count of I1 will become 6. Okay, so you can see in the diagram itself, I1 is having a value of 4 here, and I1 is having another value of 2 there. Okay, so in this fashion you can generate this tree, and you can see here from the table or from the index, all the nodes has been marked from the has been directly linked from this table. So whenever we want to fetch that value, or whenever we want to find a count of a particular item set, we can move from the link only, and we can traverse a path to find the total count. Okay. So this is the way in which my FP growth is following its algorithm to build up the tree. You can see there are chains of nodes, and all the nodes has been linked with this chain, and it has been depicted in the figure. Okay, now we will see some benefits of this FP tree structure, and this follows up those two property. One is completeness, another is compactness. It preserves complete information for frequent pattern mining. You can see if we can perform the scanning of the database once, and if we can come up with the count value, so we can if we just can build up this tree structure, and from that structure only, with the help of the linked nodes, we can find out the pattern, and we are not discarding anything. So from the pattern itself, we are having a total picture of the total database, and we can select the frequent pattern, whatever the minimum pattern we are, if we set, we can mine accordingly, and the mining, how to mine this tree, we are going to see it in the next class. We will see it. And it follows one more property, that is compactness. It reduces irrelevant information, okay, and items in frequency descending order. So whatever the whichever is the most frequently occurred item, that is going to be shared more likely, okay. And these are the benefits, and in the next class we are going to start from this one, that is how we are going to mine this FP growth tree. And again we are going to see some evaluation of patterns, and this FP growth will result in a very means it is a very efficient algorithm, right? We will see it, that how it is going to mine in the next class. Thank you.